In this podcast, we're going to take a look at what things affect whether or not a reaction is spontaneous or thermodynamically favored. In the last several sections, we looked at what happens with enthalpy or heat. And what we need to do is not look at just what's happening with enthalpy, but also what's happening with entropy, and combine those as Gibbs free energy to determine whether or not something will react or not. Okay, so we're using the term here spontaneous or thermodynamically favored. Last year we always talked about spontaneity. This year College Board is trying to get us to use the term thermodynamically favored, which really means the same thing. So in order for a reaction to be spontaneous, there's a couple of things that will impact that. One, of course, is the enthalpy, which we've been studying. And as you know, we've been talking about looking at the change in potential energy from reactions to products, and looking at whether or not a reaction is likely to occur. And what we concluded was that if the delta H is negative, which means the reactants have moved to a lower potential energy, which is generally favored, it's why reactions occur, that they are exothermic, and that is a favored reaction. It's more likely to occur. But we also have to look at this concept of entropy. Entropy is S, the symbol for it is S, and it's a measure of disorder. Lots of different terms are used. Sometimes it's dispersal or number of microstates, and it's a way of thinking about the what happens to the system. So the more disordered, if you imagine I had a deck of cards in a card box, those cards are going to be very well ordered, especially if I put them in there by all aces and all twos. But if I drop those on the floor, they are more disordered. That's all we're talking about. This is more disordered, right? It has a higher entropy than the cards did in the box, okay? And the universe tends to go towards more disorder. If I drop a roll of pennies on the floor, they're not going to order themselves. They're going to end up being disordered, okay? So the more chaos or disorder, the more thermodynamically favored we are. Okay, so any increase in disorder is favored. Okay, so and we can think about that as less condensed states. So for instance, a gas is more disordered than a liquid, which is more disordered than a solid. A solid is very condensed and organized, gas much less so. So a gaseous state is more favored. It has a higher entropy. Okay, for something to be thermodynamically favored or spontaneous, we need to look at both the decrease in internal energy, so delta H being negative, being exothermic, as well as entropy increasing, makes something thermodynamically favored. Okay. So if we go back and remember, the first law of thermodynamics says that energy is conserved, right? Well, the second law of thermodynamics says basically that the dispersal or disorder of the universe is always increasing, right? So delta S is always increasing. That's basically what it says. The third law says that, this seems kind of strange, but it says the entropy of a perfect crystal at 0 Kelvin is 0. This is, remember, absolute 0, which theoretically cannot be achieved. So the only thing that can have entropy that is 0 is a perfect crystal at 0K. In other words, the S of elements is always going to be positive. Okay? So